All right, hello and welcome back to another ALEKS explanation video. This was a requested topic, so thank you very much for the request. I get to these as quickly as I can. Sometimes it's quicker, sometimes it's slower, but thank you again. Please keep those requests coming. So this is an ALEKS topic that's called calculating key distances in the BCC unit cell. You can see that I've already annotated a few things, and I'm going to definitely talk through a number of different aspects here for this topic. I'm going to go through two specific examples, and I'm also going to talk about if you have any cases where the radius of the atom is brought into play or is asked about, and how to incorporate that into your answer, basically, or to understanding what's going on here. So neither of these two examples talk specifically about the radius, but I will talk about that if you do have an instance of this topic that asks about the radius. We'll talk about how that is incorporated basically to this topic. Okay, so let's go ahead and get started with this one. So the first thing that I wanted to just point out is the different annotations, the starting points that I've written out, reminders for myself. BCC means body-centered cubic. I want to have a good idea of what that means in terms of a picture. Obviously that's the one that's most challenging to draw. But the take-home message here is that if I draw a line from my front top corner to my back lower corner, that line is going to go directly through this body-centered atom. So there's going to be an atom in the middle. And then that line that I'm drawing from the blue dot to the red dot, there's going to be a floating atom sort of in the middle here. And that's going to have implications. Basically, the reason why that's interesting is if you are asked about the radius. So this distance between the front top corner and the back lower corner, that goes directly through that body-centered atom. And again, it has implications for the radius of the atom when we're talking about these distances. So we'll talk a little bit more about that later on in the video, but that's the significance there. The other information that we're given here, the distance between the green dot and the red dot is 0.68 nanometers. And then that's going to be the distance for the other edge lengths as well. So this is a cube. So that's going to tell us if this is 0.68 nanometers, that means that this edge length is also 0.68 nanometers. It also means that this is 0.68 nanometers as well, right? So this distance here from the top to the bottom. So basically at this point, this becomes a geometry Pythagorean theorem problem. So a squared plus b squared equals c squared for a right triangle. And in this cube, we've got a lot of right triangles, right? So what we're looking for is this distance here. We're going to call that y. So the distance from the blue ball to the red ball, that's what we're looking for. And I'm going to call that y. And so basically what I'm looking for now is how can I draw some right triangles so that I can use the information that I have in order to figure out what this distance is here. So the key right triangle to draw, I'm going to draw a dotted line from the front lower corner to the back lower corner. And hopefully you can start to see that there is a right triangle here where I'm going from here to here and then back up to the top and then back down. That is a right triangle. I know that my picture doesn't make it as obvious as it should be, but that is a right triangle. So if I can figure out this distance here, this dotted line distance from the front corner to the back lower corner, then I will have the information that I need essentially to apply a Pythagorean theorem to figure out what this distance y is. Now, hopefully you can start to see there's actually another right triangle here. Because this is a cube, from this dot to over here, that's another right triangle. And I know both of those edge lengths, 0.68 nanometers, because it's a cube. So then with that information, I can actually use that to solve for what this distance is, this dashed line distance is here, and then ultimately be able to solve for y. So let's go and do that. I'm going to redraw some of these right triangles to hopefully make it at least a little bit clear what we're talking about here. So this is a right triangle. So this is this dot here. These are both 0.68 nanometers. And I can solve for this distance. We'll call this distance x, right? So this distance from here to here, we'll call that x. And this is basically just a redraw of this right triangle here along the bottom of that cube. So 0.68 squared plus 0.68 squared equals x squared. We can go ahead and solve that for x. That's going to give us 0.96 0.1665 nanometers. So I'm carrying all my sig figs here. I'll just round at the end, but since we're doing a number of calculations, it's good to write those out. So that's our distance x. And now we have all the information we need essentially to solve for this distance y. So I'm going to redraw that. This is this first edge length here. Then we've got our dotted line going back to there. And then that's connected with y. And then this is a right triangle. So keep in mind, I know it doesn't look like a right triangle, but this is a right triangle because we're sort of working in 3 dimensions. It might be helpful. So if you've got a small tissue box, like one of those cube tissue boxes, I used to sort of mark up on those to show, which triangles we're looking at. That might be helpful. But basically this is a right triangle, along the bottom because we're sort of going in 3 dimensions. It's going away from us. So I know it doesn't necessarily look like a right triangle here, but trust me, it is. This distance is x, that's 0.962. And then this distance here is 0.68. And we know that again, because it's a cube, right? Because all of our edge lengths have to be the same because it's a cube. So now we've got the information we need to solve for y. That's going to be 0.68 squared plus 0.961665 squared equals y squared. We can solve this for y. And we get a value of 1.18 nanometers, which we're going to round to 1.2 nanometers. We've got 2 sig figs here, and we want to have 2 sig figs in our answer. So that is our answer. Oops, can't see it. That is our answer for this distance y along this line here from the blue dot to the red dot. Now, while we're at it, let's talk about the radius. So I'm going to redraw this line, just the line over here, which we know is 1.2 nanometers. And I'm going to draw in our different atoms that would be, along this line. That's supposed to be a circle. I know it doesn't exactly look like it, but it is. And then I'm going to draw in our other atoms that would be at the corners, right? So each corner is going to have an atom. And then in the middle, since it's body-centered cubic, there's going to be another atom. So if I break this up from the middle, I have the equivalent of 4 radii. So this is 1 radius. So radius is half, right? Half of the diameter, if these are spheres. So this would be 1, this would be 2, this would be 3, and this would be 4. So the significance of it being body-centered is that this distance between the front upper corner and the back lower corner, that distance is equal to 4r. So in all of these problems, we're going to be doing similar things here, Pythagorean theorem, right triangle, so on and so forth. The only other piece of information you really need to know is that this distance between these corners, right, the opposite corners, top and bottom, is equal to 4r. So if you wanted to find the radius for this, system, you would just say that, 1.2 nanometers is equal to 4r. Solve for r. 0.3 nanometers is the radius of the atoms in this system. So hopefully that makes sense. If not, certainly leave a comment below, and I will try to clarify. Let's go ahead and do one more really quickly. So this one is similar, but just very slightly different. We are now given the distance between the blue ball and the red ball, and we're asked to find what the edge length here is. So basically we're going to do what we did in the previous one, but just do it in reverse essentially. So again, I'm going to draw out, I always like sort of redrawing the cube just so that it's sort of standardized for the way that I do it, the way that I think about it. Even though they give us this sort of nice picture here, we are given this distance here. Right, so we're given that distance, that's the 251 picometers. You have to keep in mind what our units that are given here are. And what we're looking for is this edge length here. So we're going to call this x. This is the edge length that we're looking for. And then we're going to sort of just start drawing in some other, right triangles. So I'm going to fill in what our cube would look like. And then it's definitely somewhat of a skill to start seeing, visualizing the different right triangles, the different lines that we're looking for. but I know that I'm going to have to figure out what this distance is from the back corner to this front corner. That's going to give me the information that I need to solve for this x, because I know that this distance here is going to be equal to, this distance squared is going to be equal to x squared plus x squared, because I see that I've got a right triangle along the bottom. So this is a right triangle. And then I can also see that I have a right triangle now right here, right? And again, you have to start visualizing these in 3 dimensions to see all the different triangles that we're looking for. And I know that this back line, I also know that that has a distance already that's equal to x as well. So sort of a lot of pieces here. Basically, what I'm going to start doing is going through the process of solving this. The information that I know is this 251 picometers from the back upper to the front one up here. I need to figure out what this distance is here, and so yeah, let's just write it out. And I know that I'm getting a little confusing here. So let's start by drawing out this bottom triangle. And again, this is a right triangle. I know that it doesn't necessarily look like it, but it is. So if this was this triangle here, then I would have x for this distance here, our unknown edge length, x for this distance here, and then we would need to calculate what this distance is from the bottom here. And that's actually we'll call that y. So then x squared plus x squared is going to equal y squared. We could rewrite y, basically solve this for y, as the square root of x squared plus x squared, right? So basically what we're saying is that this distance between here to here, if we call that y, that's going to be x squared plus x squared, square rooted. So solving this essentially for y. Now, basically we can use that information to figure out what is going on up here. So let's redraw that triangle. And again, that is going to be a right triangle. I know it doesn't exactly look like it, but again, we're in 3 dimensions here. This distance here is going to be x. That is the edge length, right? So we know that that's the edge length. This distance here is the square root of x squared plus x squared. So that is our distance y. And we figured that out earlier over here because we know that there's this other right triangle. And then this distance is 251 picometers. So I could use this information to figure out, again, well, if that is x squared, x squared plus x squared squared equals 251 squared. So if this is the distance here, x, and this is this distance, y, we know that y is x squared plus x squared, take the square root. So that's that distance here. Now we've got one equation with one unknown. X is our only unknown. So now we just need to solve this for x. And we can do that by sort of rewriting this and getting rid of this, if this is square root and this is squared, x squared plus x squared equals 63001. This we can combine to 3x squared equals 63001. And then just sort of finish solving this for x equals 144.9 picometers. We're going to round that to 145 picometers. So that is my answer. And I know my explanation was a little bit so let's sort of walk through it a little bit one more time. So basically, we've redrawn it. We're looking at our different right triangles, figuring out what information do we have, what information do we need. X is our unknown, X is what we're actually looking for. So then it's just a matter of figuring out, well, if this is this X edge length here, that would be this X edge length here. That allows us to solve for this distance here that we've called Y. This equation right here, right, is going to be how we solve for that distance Y. But we want to have just one unknown, and we know that in this triangle here, this distance is also X. So I want to basically rewrite this Y in terms of x, right? So that's what I'm doing here. Y equals x squared plus x squared. Take the square root. And then I can use that with this other triangle here that we're seeing right here, which is again another right triangle. And I can use that in order to solve for x ultimately. So I'm just basically rewriting everything in terms of, I know that this looks funny. My drawing skills leave something to be desired. But this is basically just redrawing this triangle here and then trying to show what all the different distances are. So again, if we wanted to talk about the radius in this case, the radius would just be, 251 divided by 4, because that's that 4r distance for the radius right here. But obviously, in this case, we don't need to worry about it. If you were given the radius, right, and you wanted to figure out what this distance is here, it would just be the radius times 4, right? That would be another way to sort of figure that out. But hopefully that's helpful, and thanks again for the request.